In the second part of this lecture on integrated rate laws, we want to expand on the topic of half-life. It's often convenient to use the half-life as a measure of how fast the concentration of a reactant changes with time. Half-life, which is, as you can see, often symbolized by T with a subscript 1/2, is simply the time it takes for the concentration of a reactant to reach half of its starting or initial value. The half-life expressions corresponding to first, second, and zero-order reactions, again remember for the general case of a reactant going to products, are shown in the table to the right. For example, for a first-order process, rate equals K times A. We know the integrated rate law looks like this in this column. The half-life expression for this first order process would be that the half-life is equal to 0.693 over the rate constant. You might ask, where does that come from? We'll do a derivation in a couple of minutes to show how we got at least one of these half-life expressions. For a second order process, rate equals K times A squared, we know the integrated rate law looks like this. The half-life expression for that second order process would be T1/2 equals 1 over the rate constant times the initial concentration of the reactant. And for a zero order process, of course, rate equals K. The integrated rate law is written here that we looked at previously. And the half-life expression for a zero-order process is T1/2 equals the initial concentration of the reactant divided by 2 times the rate constant. Now each of these half-life expressions, as I mentioned, can be derived from the corresponding integrated rate laws by just substituting T1/2 for T and the concentration of A0 divided by 2 for AT. That probably makes no sense, so let's show you an example. Let's derive the expression for the half-life of a second order process. The integrated rate law for a second order process is written right here. It's 1 over the concentration of A at some future time t minus 1 over the initial concentration of A equals the rate constant times the time. Now what we're going to do here is remember our job is to find the half-life, the time it takes for half of the initial concentration to disappear. We're going to say the concentration at some future time t we're going to set as half of the initial concentration, and we're just going to substitute T1/2 for T. So literally what we're going to do is make T here T1/2, and we're going to put A0 over 2 in for AT in this expression. If we do that, we have 1 over A0 over 2 minus 1 over A0 equals K times T to the 1/2. Solving for T1/2, this expression 1 over A0 over 2 simply turns into 2 over A0, and now we simply have to subtract 1 over A0, set it equal to K T1/2. 1 over A0 would be the result, equals K T1/2, and now we'll solve for the half-life, or T1/2, by dividing both sides by K, and we get that the time it takes for half of the initial concentration to disappear is equal to 1 over the rate constant times the initial concentration, which is what we have right here. The half-life expressions for the first order and the zero order could be obtained in a similar way. Now, in what appears to be a strange result, only the half-life expressions for the second order and the zero order cases contain the term A0. In other words, the half-life of a first order reaction does not appear to depend on how much reactant you start with, which seems to be, or I think can be, a confusing result, because the rate of the reaction, the initial rate at least, is certainly going to depend on the initial concentration of the reactant, but the half-life does not have that in the expression. Now, if this didn't bother you before I just mentioned it, go back to not letting it bother you, but we'll use this odd result in an interesting way in a future slide. Here's an example problem involving half-life. Recall the reaction that we examined in the previous slides, NO2 decomposing to NO and oxygen, and we determined that this reaction was second order with respect to NO2 and that the rate constant was 0.5431 per mole per second at the stated temperature from a linear plot of 1 over the concentration of NO2 versus time. Now, if the initial concentration of NO2 was 0.01 molar, what would be the half-life? What's the time it takes for half of this to disappear? Well, in the table on the previous slide, we simply find the expression for the half-life of a second-order reaction. The half-life equals 1 over the rate constant times the initial concentration. Now, given in the problem is the rate constant and the initial concentration. So this should be a simple matter of just plugging in the values. If we do that, we get 1 over 0.5431 per mole per second times 0.01 molar, which gives us 1 over 0.005431 per second, which, if you do the math here, comes out to 184 seconds. So the NO2 concentration would reach half of its initial value, in other words 0.00500 molar, in a little over 3 minutes. Here's another example of a problem involving half-life. Radioactive decay can be described by first-order kinetics. The half-life of the radioactive isotope iodine-131 is a little over 8 days. It's 8.021 days. Now, using this half-life, we could ask what mass of iodine-131 would be left after 24.063 days, which, not coincidentally, is exactly 3 half-lives. 3 times 8 times 8.021. If the initial mass of iodine-131 was a gram. So we're asking, if you start out with 1 gram of iodine-131, how much is left after 24.063 days, which turns out to be exactly 3 half-lives? Well, first of all, we need to recall that the equation describing this decay was given in the previous lecture. We have iodine-131, and 53 is the atomic number of iodine, the number of protons in the nucleus. 131 is the mass number. Iodine-131 can decay to xenon-54, mass number 131, and this results in the ejection of an electron, which we call a beta particle. Now, as an aside here, if you're not familiar with radioactive decay processes from high school chemistry or any previous course, what's happening here is a nuclear reaction. That means it's a reaction that originates in the nucleus of the atom. In fact, we say here that iodine-131 is undergoing a transmutation to xenon-131. One element is turning into another. And the way this would happen here is that a neutron in the iodine-131 nucleus is converted into an electron and a proton. The electron is ejected from the nucleus and is called a beta particle when that happens. That's what makes this process dangerous, to be exposed to those beta particles. And the new nucleus now has an extra proton. So the nucleus now is 54 proton, and as you recall, the element is defined by the number of protons in the nucleus, xenon has 54 protons. So we've turned iodine into xenon and ejected a beta particle. Now, since this is a first order process, we could write rate equals the rate constant times the concentration of our reactant. If you wanted to be technical here, we probably should drop the brackets because we're not really dealing with concentrations, we're just dealing with masses. So I'll make the brackets look different here and write the rate expression like this. And so we assign these parentheses as mass in grams. And we can actually solve this problem quite quickly if we just realize from the definition of half-life that what we're doing is cutting the original 1 gram in half 3 times. So if we start out with a gram and we wait 8.021 days, which is 1 half-life, we'd have half of what we started with left, 0.5. If we then wait another half-life, another 8.021 days, we'd have 0.25 grams left. And if we waited the third half-life, another 8.021 days, we'd have 0.125 grams. So that would be the amount remaining after 3 half-lives. Let's take a closer look at this first-order decay process. Recall from slide 11 that the half-life for a first-order process, which is what this is equal to 0.693 over K. Now it's stated above that the half-life for iodine-131 is 8.021 days. Therefore, if we do use this expression and we know the half-life, we could solve for the rate constant. So let's do that. So what I'm doing here is simply rearranging, solving for K, putting in the half-life, and we get a rate constant of 0.0864 per day. Now, we have the rate constant in these strange per day units for the first order process describing the decay of radioactive iodine-131. We already solved the problem at hand up here by just using common sense, and we didn't even use an equation. So why are we doing this? Why is knowing the rate constant helpful? Well, it is helpful, and let's see why it might be. Again, here's our radioactive decay process. Here's the rate law, our first order rate law. The integrated rate law for this would be the ln of the amount left at some future time t minus the ln of the initial amount equals minus kt, because this is the integrated rate law for a first order process. Now, whether we're writing the rate law or the integrated rate law, k is 0.0864 per day. We determined that from the half-life on the previous slide. Again, what's the point of all this? We're trying to show that for a first-order process, the half-life is independent of the initial concentration, or in this case, the mass of the reactant. And the way we can do that is we're going to use our rate constant here to actually calculate the time it takes for half of the initial amount of iodine-131 to decay for 3 different initial masses. So we're going to basically calculate the half-life if we start with 20 grams or 14 grams or 3 grams. Let's try this out. If we start with 20 grams and we use the integrated rate law, we'd say the natural log of the amount left at some future time t minus the natural log of the initial amount equals minus kt. If we solve for t, for time, we'd have this expression. And we know that the starting amount in this case is 20 grams. And the amount after time t is 10 grams. Well, why is that? Because remember, we want to calculate the time it takes for half of the initial amount to disappear. In other words, we want to calculate the half-life. So the time it takes for half of it to disappear would be the natural log of 10, which would be the amount at time t, minus the natural log of the starting amount divided by the rate constant. If we do the math here, we end up with 8.02 days. And by definition, that's the half-life because that's the time it takes for half of this to disappear. If we do the same calculation, only we start with 14 grams, and we go through all the same iterations, we find out that the time it takes for 14 grams to go to 7, in other words, for half of the initial amount to disappear, is again 8.02 days. If we start with as little as 3 grams, and we do the same calculation, we get 8.03 days. That's just a rounding error. So in other words, the half-life for this first order process does not depend on the initial amount of material. Whether we started with 20 grams, 14 grams, or 3 grams, the time it takes for half of that to disappear is the same. So it makes sense that the half-life expression for a first order process does not have the initial concentration in it. It does not depend on the initial concentration. Now, both the second and zero order processes have half-lives that are dependent on the initial concentrations of reactants. So for second order, there's the initial concentration in the half-life dependence. The half-life gets shorter with increasing initial concentration. For the zero order process, the half-life actually gets longer with increasing initial concentration, which might seem a little strange at first, but that's what the math tells us. We need to discuss one more thing before we leave this lecture. The zero order reaction, if you think about it, at least when I think about it, seems to be on the face of it really strange. How could a reaction rate have no dependence on the concentration of the reactant? Remember, for a zero order reaction, rate equals K times A to the 0 power, which means rate just equals the rate constant. No dependence on the initial concentration or on the concentration of A, the reactant, at all. And then what's even stranger is if a zero order reaction, the rate of a zero order reaction, has no dependence on the concentration of the reactant, why would the half-life of a zero order reaction depend on the initial concentration when the rate of the reaction has no dependence on the concentration? So this seems to be pretty twisted. So let's address these issues one at a time. First would be, how could a reaction rate have no dependence on the concentration of the reactant? Well, suppose that a reaction where A simply goes to B, that of course fits our profile, a reactant going to products, can only occur when A attaches to a metal surface. When all the available binding sites on the metal surface are occupied, it will not matter what the concentration of A is above the metal surface. The reaction rate will be independent of the total concentration of A. Now, these cartoons here are supposed to help with this. So let's look at the top half of this figure. What we have here is a lot of A approaching a metal surface, and A attaches to the metal surface, and you'll notice that all the sites are taken. So all of these A's are hanging around because these sites are all taken. The real reaction occurs with a rate constant K right on this metal surface, the interaction between the metal surface and A is turned to B, and of course there's still A hanging around. And so let's suppose now that there are fewer A molecules above. All the sites are still taken, and all of these are turned to B. What we're trying to show here is that it doesn't matter what the total concentration of A is. the reaction can only go as fast as A going to B on the metal surface. So what we say here is, despite there being a higher total concentration of A in the upper reaction, both reactions occur at the same rate. The rate is totally governed by the interaction of each A with the metal surface. So again, the overall rate does not depend on the total concentration of A. It only depends on the interaction of A with the metal surface and going to B. So now we can say, okay, the rate overall is a function of just the rate constant. It's not a function of the total concentration of A. Now you might ask, is this all made up? Could this not possibly happen? Well, of course it can happen. A catalytic converter in your car converts carbon dioxide from your car engine to CO2 via reactions of gas molecules sitting on metal surfaces in your catalytic converter. So if you don't want that to happen, just take out the catalytic converter and then you'll get in trouble, because I think that's illegal. Let's take on the half-life issue on the next slide. How could the half-life of a zero-order reaction depend on the initial concentration when the rate of the reaction has no dependence on the concentration of reactant? Again, let's put up these cartoons from the previous slide. If we think of the half-life as being the total time it takes for half of the total A to be converted to B, then it would make sense that the more total A is present, the longer it will take to transform half of it to B. So if we start out with more total A, as on the top, then it's going to take longer for this metal surface reaction to turn all of the A to B, because there's more A to turn. So as soon as these A's are turned to B's and the B's leave the metal surface and more A come on the metal surface, what you're measuring is the time it takes to get rid of all of the A, the total A. So the actual rate is independent of how much A is there, but the time it takes for all of the A to disappear does depend on how much total A is present. So hopefully now it makes some sense as to why the rate could show no dependence on the concentration of A, but the time it takes for half of the A, total A, all of the A to disappear would depend on how much A is present. So you might ask here, aren't we making some assumptions? For example, aren't we assuming that the rates of A attaching to the metal surface and that of B leaving the metal surface are fast compared to the rate of transformation of A to B on the metal surface? And the short answer there is yes. And I'll just say that's why corporations hire chemists to sort all of this out.